In this hands-on, we're going to explore data processing pipelines with chained generators in Python, focusing on how Python's iterator chains can be effectively utilized in different applications. We begin with our streaming log processing example as usual, demonstrating the creation of a basic streaming log processor using generator functions. The read log entries function has one argument, log file. This is a generator that reads log entries from a file, yielding one entry at a time. It exemplifies what we call lazy evaluation in Python, processing data as needed. Next, we have the filter log entries function that has two arguments, entries and error code. Its job is to filter log entries based on the error code. Next, we have the analyze logs function, which accepts entries as one argument. It performs a simple analysis on filtered logs. Here we have analyzed entries populated with the output of analyzed logs, which accepts filtered entries. Filtered entries were previously populated by the output of the filter log entries function, which accepted all entries as an argument, where all entries was populated with the output from read log entries. In our next example with genome pattern recognition, we have the read genomic sequences function that accepts a file path for an argument. We have the find patterns function, which has two arguments, sequences and pattern. It searches for specific patterns within genomic sequences. Then we have the report findings function, which has one input argument called sequences, and this function reports the findings from the pattern search. For those of you who are interested, there is a more advanced example further down in the not so simple example 2 section with the code block down here. Moving on to our simple stock price anomaly detection example, we have read stock prices, which accepts a file path as an argument. Its job is to read stock price data from a file. Then we have the calculate moving average function, which has two arguments, prices and window size. Its job is to compute the moving average. The next function, called detect anomalies, has two arguments, prices and threshold. Its job is to flag anomalies based on a set threshold. Let's go through another simple example, this time using itertools. We'll use the compress function imported from itertools to filter logs based on a selector. Here we have a list of logs, an error selector that is essentially populating a list with true or false. We then use compress to filter the logs, with the first argument being the logs themselves and the second argument being the error selector. In the second example to do with genome pattern recognition, we're using group by, where it's employed to categorize DNA sequences based on the presence of a pattern. Here we'll import group by from the itertools module. We'll define some sample DNA sequences in a list over here. Then we'll create a function to categorize DNA sequences based on the presence of a pattern. Using the group by function from itertools, we'll then group DNA samples by pattern presence. And finally, for each category and sequence found in the group DNA, we'll print the category and the list of sequences to the console. In the third example, where we're covering stock price anomaly detection again, we'll demonstrate the use of iSlice, importing it from the itertools module to analyze a subset of data, specifically recent stock prices and their moving averages. We have a function here called calculate moving average that has two inputs, prices and window size. It calculates the moving average of stock prices. We then define a sample list of prices, a window size, and calculate the moving averages on that prices list using that window size. And finally, we use iSlice, imported from itertools, to analyze recent stock prices and their moving averages. As in previous hands-ons, where we've taken things up a notch, we now have some not-so-simple examples using itertools. In this first example here to do with streaming log processing, we use chain to combine logs from multiple sources and group by to group logs by severity. In the second example over here in genome pattern recognition, we use cycle and iSlice from itertools to simulate a stream of DNA samples and analyze a fixed number of samples. In the third example to do with stock price anomaly detection, we employ the product function from itertools to create a Cartesian product of prices and thresholds for anomaly detection. And in the final and fourth example, to do with stock price anomaly detection, here the revised calculate moving average function accepts the prices iterator and a window size. and it calculates the moving average of stock prices from this iterator. First, a prices window is composed, utilizing the iSlice method from itertools, applied to the prices iterator and the window size. And while the prices window exists, this function will continuously yield the sum of the prices window divided by the window size. The rest of the code in this block explains the entire functionality of the example, the revised detect anomaly function, sample stock price data declaration later on, and how the T function is used later to create two iterators from the list of prices, how the function goes on to calculate moving averages for the second iterator, how the prices are paired with their moving averages to detect anomalies, and finally the prices and averages in the calculated anomalies printed to screen. A lot has been covered in this hands-on, and clearly we haven't gone through the entire code line by line, but I do encourage you to download this Jupyter notebook and study the code through each step to build your intuition further about the combination of various itertools functions into chained operations and functional units that involve more than one function to perform the same activity in a more memory and space efficient way. This hands-on should hopefully have provided a comprehensive understanding of how Python's iterator chains and the itertools module can be applied to practical data processing tasks, such as the ones highlighted here, enhancing your code's efficiency, readability, and scalability in any real-world scenario. Thank you for your attention as always. See you in the next lecture.